Thank
I
you.
should remove this. Okay, let me start by thanking the organizer for inviting me to present my talk. I'm going to give a talk on holographic complexity with a cutoff. This work is based on the following paper appeared a month ago, which is actually a follow of the two others paper. Let me start to say a few things about the complexity and why we need complexity or some notion of complexity. Of course, already you have heard from Ali's talk about the complexity and because of continuity, I will also give some introduction on complexity, but it would be very brief. Let me start with saying a few words about general idea why we need complexity. It is of course, it is of great interest to understand the physics behind the horizon. Of course, its understanding might need eventually to understand full knowledge of quantum gravity. ADS-B correspondence could provide a useful tool to explore at least certain features of physics beyond the horizon, working within this framework of ADS-CFT correspondence. The problem may be rephrased as the how to construct a spacetime from the boundary field theory. In this context, holography entanglement entropy was found useful to explore this possibility, though it might not be enough. And maybe we need some things more, which it is known as a complexity, or is named as complexity. To explain why we need some sort of complexity, let me just say a few words about the well-known thing in ADS-CFT correspondence. In ADS-CFT correspondence, we might have a black hole, and we know that the black hole could provide a dual description for the conformality at the finite cutoff. This is a static solution, of course, therefore there is no time dependence phenomena. According to ADS-CFT correspondence, everything the gravity should be understood from field theory and vice versa, including the black hole interior. But the system is static. Now, suppose we start from the space which is nothing there. It could be a flat space or a synthetic space, and just inject some energy or some matter there to make a black hole. And then with adding matter, then you may create a black hole. And the point is that the process of making a black hole is a time-dependent process. But the point is, as soon as a black hole was formed, then we have the thermalization, and therefore we have the static solution. But the volume inside the horizon keeps growing linear with time. And if we look at the ADS-CFT correspondence, from one side we have a static solution, but from another side we have something which time dependent, is growing with time, which is the inside of a horizon, and would expect that the something time dependent would appear in this context. To be more precise, the boundary field theory reaches a thermal equilibrium very quickly, while the Einstein-Rosen bridge continues to grow on time, in longer time scales. Therefore, there must be some quantity in the field theory that corresponds to this information, which is time dependent. Saska introduced holographic complexity as a boundary entry whose growth corresponds to the evolution of this bridge, Einstein-Rosen bridge. This was the idea of Saska to introduce some new thing which is time dependent in the context of ADS-CFT correspondence. And motivated by this observation, he defined something which is called complexity, and this in the new literature it is known as complexity equivalent to volume, which says that the complexity of the boundary state is proportional to the volume of the maximal codimension one bulk surface that extend to the ADS boundary and associated to the time slide sigma on which the boundary state is defined. And this is the expression for the complexity. This is known as the CV proposal. Of course, there is another proposal, as we have heard in the previous talk, which is called volume complexity equal to action, which means that we have to, in this proposal, we compute action, on-shell action, the particular region of the space-time known as the Wheeler-DeWitt patch. And the Wheeler-DeWitt patch is actually domain of dependence of any Cauchy surface in the bulk whose intersection with the asymptotic boundary is a time slice. That's the Cauchy slice. I'm not sure if whether you can see my pointer, but in any case, this is the time slice here, and this is the Wheeler-DeWitt patch here, which is known as drawn as blue region, and we have to compute on-shell action in this region of a spacetime. And the action, by the action, we mean that different term which appears in the expression of the action. The known term is the bulk term, and there are several other boundary terms associated with the time log, space log, or null boundaries. There are some action associated with the joint points where two boundaries intersect, and also we have some counter term which has to do with the fact that there is an ambiguity to define the norm for the null vector, and this ambiguity, to remove this ambiguity, there is this counter term one has to add to the action. And if you want to compute the complexity, according to this proposal, we have to evaluate this on-shell action here, this action here, on this Wheeler-DeWitt patch. To do this, I put some cutoff here, some cutoff at infinity. I mean that at the boundary, which in my notation is at the r equal to 0, and also some cutoff at singularity, which in my notation it's r equal to infinity. Therefore, we set two cutoffs and compute on-shell action on these blue regions. And to do this, one needs to have this bulk term and some joint term here corresponding to these points, which come from this term, and also some boundary terms corresponding to this null boundary, some space-like boundary as well there. If one computes action for this particular eternal black hole, what we get is this expression for this complexity growth. This expression for complexity growth and is the energy of the black hole, and F is defined in this term. F is the blacking factor in the apprehended expression of the geometry, and F tilde is defined by this expression. At late times where Rm approaches Rh, this term vanishes, and we end up with some constant here, which is twice of energy that is known as Lloyd bound. Actually, if we look at this expression here more carefully, what we get is the behavior.
Can I have a quick question before you go there?
Sure.
Yeah.
Sure.
So in your, not the previous slide, but the slide before that, there was a term which has a parameter A, this ADS.
Yes.
So what is this JD?
Okay, JD is the volume of the intersection point. I mean this point, and this point.
Oh, so these are the special terms which you need if you have corners.
Yes, exactly, okay. Yes.
Got it.
I didn't write the, okay, here is the expression of A there, which is logarithm of K1 and K2, and K1 and K2 are as corresponding null vector to this boundaries there.
Okay.
Okay, thank you. Okay, so if you look at this expression more carefully, what we get is something like this. It means that although it approaches some constant here, which is twice of energy, which is well known in the bound, well known as a Lloyd bound, but it approaches this bound from above. It means that the holographic complexity defined in this case somehow violates the Lloyd bound. It is bigger than this twice of energy, but the point at the end of the day, I mean that at late time, it approaches a constant, which is given by the expression of the Lloyd bound. Okay, That's what my review of the how to compute what is the complexity and how to compute the complexity. And now let's consider the case where we put this theory at the finite cutoff. By finite cutoff, I mean that we keep this RC's constant is fixed and finite. This is a good reason to say this situation, and it provides a holographic dual for a conformal filter deformed by certain deformation known as TT bar deformation. Just to give a few comments about that. Although TT bar deformation, which is a really irrelevant operator, it was shown in this paper that the resultant theory after deformation is still exactly solvable. And if you start from the conformal field theory deformed by this irrelevant operator, for the conformal field theory on the circle with this length L, the energy level En, and the conformal dimension delta N and delta bar N, the expression for energy can be given exactly and explicitly, which is given by this expression here. And here the definition of M and J, the corresponding here. This is for two-dimensional conformal field theory where everything can be computed rigorously. Going to a higher dimension, we don't have such a description from field theory, but based on what we get from the field theory in two dimension, people have proposed something for TT formation, TT bar deformation for higher dimension. In this case, they consider certain combination of the energy momentum term and deform the action by this center by this certain deformation here. And this defined deformation, deforming the bulk action by this term defines, holographically defines a deformation, a TT bar deformation for D+1 dimensional conformal field theory. And in this case, if you start from this solution for the black hole, then the spectrum for the deformed theory is given by this expression. And there is a relation between mu here, with the deformation of the bulk theory, and this of the action, and RC, which is the cutoff, radius cutoff of the ADS. There is a relation between there. Now the aim is to compute complexity for such a system in the case, which means that complexity for the case we have finite cutoff. It means that we have to redo the same computation I did before. Of course, I didn't show you the explicit computation. I just showed you the final result. But in principle, we have to go to the all computation. But the assumption that RC is kept fixed. Now the point is, since the solution we got here was independent of RC, therefore one would simply expect that in this case, at the late time, the complexity didn't change, doesn't change. Therefore, it seems that the UV cutoff doesn't change anything in this scenario. There is some observation. Holographic complexity growth obtained by the unshelled action evaluated in the Wheeler effect is insensitive to the UV cutoff at the late time. This is what I showed you here. That's the expression. There is no RC there, which is UV cutoff. On the other hand, one would expect that the late time growth is given by the physical charges, which indeed depend on the UV cutoff. Therefore, there is a conclusion. One may conclude that either unshelled action does not compute complexity because there is a conflict between the computation I showed you or present the result and the thing we would expect to have the Lloyd bound and some which depend on the physical charges which depend on the UV cutoff. There was some conflict between these two observations. So either unshelled action does not compute complexity or the late time is not given by the physical charges, or in our computation, we have missed something. We have to redo our computation. Based on what we are in the literature, people believe that the unshelled action evaluated on Wheeler-DeWitt is going to be some kind of complexity, and people believe that at late times is given the late time is given by the physical charges, which depend on the UV cutoff. Therefore, there should be something wrong with our computation or my computation here. Therefore, let's redo our computation, but more carefully. To do this, let me just show you, we have two cutoffs here, one at boundary and one at singularity there. And I kept this fixed to have the theory at final cutoff, but at the end of my computation, I send R0 to infinity because I want to remove this cutoff. But for the moment, suppose we keep both of these cutoffs fixed. And if you go to all computation, but keeping all these two cutoffs fixed, this is what we get for the expression of the late time of action growth or complexity growth. Beside the term we had before, we have some extra term which is given by this R0, which is a cutoff at singularity there. So if there is a room here, because we have some extra term, there is a room to somehow find an expression for complexity which depends on cutoff. Remember that we would expect that at late time, the complexity growth or action growth should be given by the energy, twice of the energy, which now is deformed by this cutoff. So if we believe that this is the case, therefore this should be equal to this one. And equating these two expressions, one gets some expression for R0 in terms of cutoff. It means that it tells you that, of course, the complexity is given by, of course, complexity can be computed by on-shell action in the relative patches, and it depends on UV cutoff, but in indirect way, in the sense that it depends on RC, R0, R0, and R0 is given in terms of RC. And this is a conclusion for this part of computation. As soon as one sets a UV cutoff at the boundary, the model itself enforces us to have a cutoff beyond the horizon whose value is fixed by the UV cutoff. Actually, such a relation should be intuitively understood from the fact that the energy is a charge defined at the boundary, while the late time behavior of complexity evaluated from the action entirely computed beyond the horizon. And it is an interesting feature of complexity that has a potential to prove the physics beyond the horizon. If it is correct, it means that the near singularity modes may be regularized through the UV cutoff to a UV cutoff. You don't need to add extra cutoff near the singularity. As soon as you fix this cutoff at the UV, it automatically gives some cutoff near singularity. Let's redo the same computation for charged black hole to see what's happening in the charged black hole. For charged black hole, we start from some Einstein gravity coupled to some gauge field. This expression for the solution, we want to compute this corresponding complexity. And actually, the complexity for this model has already been computed in the literature. We have this Penrose diagram there, and this is a relative patch here. And for the complex, one can go through the computation to have all terms I showed you and compute all of them. At the end of the day, what we get for at late time for the complexity is given by this expression. Of course, you can write this in terms of the physical charges, masses, and other thing. And this is the expression for late time of complexity of for charged black hole. Now the aim is to put some cutoff here and redo the computation for the charged black hole when we have cutoff. Then we set cutoff here. Here we have, sorry, let me just, here we have two possibilities to set the cutoff beyond the horizon. If we assume that the same as neutral charges, whenever you set some cutoff, it enforces us to have some cutoff beyond the horizon. If we assume such a thing happens here, there are two possibilities. Either the cutoff should be behind the inner horizon, I mean this here, which is some time-like cutoff, or it could be set between two horizons, which could be some space. Should be some space-time cutoff here. For the moment, I assume that the cutoff should be put in between two horizons. And at the end of the day, we will see that everything is consistent. Therefore, our assumption should be correct. And going to all computation, so assuming this, we have some UV cutoff there, it enforces us to have some cutoff, and we assume that this cutoff should be put between two horizon and this cutoff here, and go to all of computation we have done before. Then we can compute the complexity for this setup with cutoff, and at the late time, what we get is this expression. Interesting enough, it has the same expression as neutral charges, and only charge dependence come from the blacking factor here, and this has exactly the same expression of them. Of course, it is evident. Therefore, it is evident that it reduces to that of the neutral case in the zero charge limit. If you set just Q equal to 0, this reduces to this black hole without charges, and this is exactly the expression we had for neutral charges. On the other hand, it also clear that from when we set the cutoff to 0, it means that in this case, R0 should approaches this inner horizon. Here, R0 approaches there. In this case, it is clear from this expression, this is 0 here. Therefore, we get this expression, which is exactly expression we had before for complexity without cutoff. But so it is believed, now it is believed that the late time behavior, this is the late time behavior. It's believed that the late time behavior of complexity should be expressed in terms of the conserved charges as energy and other things as we had in the neutral cases. Remember that this is given by R0, R0, which a priori is not, is a priori, there is no relation between R0 and physical charges. But they believe that, one believes that the complexity should be given at late time, it should be given by physical charges. And therefore, there must be some relation between R0 and UV cutoff, the same as we had in the neutral cases, so that the above expression for the late time growth of complexity can be written entirely in terms of the conserved charges defined at boundary. To find this expression the same as what we did in the neutral case, the thing with this QS is the Lloyd bond. Therefore, we have to find some appropriate Lloyd bond or Lloyd expression for the complexity, complex growth for charge in order to read this late time behavior of the complexity. And from this, one may find some expression for R0 in terms of RC. So let me give some general idea, general review of a Lloyd bond. The Lloyd bond gives an upper bound on the growth rate of the quantum complexity of any physical system, which is given by this expression, which means that it tells you that the complexity growth is smaller than twice of energy of the system. In the context of holography, this at late time, this inequality saturates, and what we get is, as showed you, that the action growth or complexity growth is given by, at late time, is given by twice of the energy or twice the mass of the black hole. It's worth noting that although we are calling it the Lloyd bond for historical reason, more appropriately, we should think of this as a bound on the complexity growth, given in terms of the conserved charge quantities at the boundary, at the holographic boundary. Therefore, in the presence of the UV cutoff, this bond will therefore be sensitive to UV cutoff. Now, let's go to a charged black hole. Although there is no rigorous expression or derivation for Lloyd bond in the charge case, but there is some proposal which almost worked with all models which have been studied so far. And this expression for complexity growth when we have the charge. Here, E and Q are ADM charges and mass. And mu plus minus formally denote the chemical potential associated with two horizon R plus R minus. It's worth mentioning that although mu minus cannot be interpreted as a chemical potential from the perspective of quantitative, but at the end of the day, everything is given in terms of R plus R minus, which and all charges can be expressed in terms of R minus and plus, and therefore at the end of the day, although this expression looks formal, but at the end of the day, everything is given in terms of physical charges. Now, if you look at this expression, it saturates in the background, and it almost gives the expected result when we compute the holographic complexity, and it also reduces to an uncharged limit when we send Q equal to 0. But it's interesting to look carefully for the case when we get neutral cases out of this expression. To get neutral case, we send Q equals 0, I minus to infinity, and simultaneously mu plus Q to 0 and mu minus Q to M. Then if you look at this expression, what's happened in this limit is that this E cancel this E, and mu plus Q vanishes, goes to 0, and we end up with mu minus Q minus mu minus Q, which is actually 2 times M according to this. Therefore, we get the right answer for the neutral case. Although we get the right answer, but it seems a little bit unnatural in the sense that we would expect that when we send our Q equal to 0 and R minus to infinity, what we would expect that the all term coming from mu minus, or this minus part, vanishes, and the Lloyd bond or expression at late time come from the plus term. But in this case, you will see that the thing comes from this inner horizon, which we are sending to infinity. It's looking a little bit unnatural. And moreover, due to this unnatural limiting behavior, it has been shown in this paper that it was argued shown that this expression I showed you here is unable to accommodate the right expression for Lloyd bond when a finite cutoff is applied to the theory. Based on these two observations, we propose a new bound or new expression for complexity growth, late time behavior complexity, which is given by this expression, which is almost the same, except that there are some extra two here, 1 2 here and 2 here. And now if you look at this expression, you realize that although these two E cancel each other, but if you compute Q equal to 0 to get neutral charges, there is more natural way to get neutral cases. In this case, when Q goes to 0, this term vanishes, this term cancels this term, and at the end of the day, you get just this term, which is 12 of energy, and it comes from this positive side. Therefore, it looks better in the sense that when we set Q equal to 0, the right answer for the complexity growth, late time complexity growth, come from this positive side. Now, if you put this system, the finite cutoff, we would expect that whatever it comes in the positive part, which is the behind the outer horizon, should change, but the thing which is inside the horizon shouldn't change. Then if you go to all this computing more in detail, then this is what we get. With a finite cutoff, we have the E plus get deformed in this deformation in this form, but the E minus remains unchanged because it's inside the horizon. And moreover, in this particular model, which we put some cutoff without the charges, we didn't deform the model with operator which has charge. Therefore, this expression for chemical potential doesn't change. and we have just deformation from, we get from modification from E plus. Putting this expression in this expression for late time, this is what we get for the late time behavior of the complexity when you have charge at the final charge black or the final cutoff. It's interesting to study the neutral case when q equals to 0. In this case, this term come from r plus cancel is 0, and this term come from r minus cancel this term, and we end up with this expression. This is exactly what we have for complexity growth at late time complexity growth for neutral case when we have some finite cutoff here. So using the expression and equating this expression to what we get for complexity here, then you get some expression for R naught in terms of RC, and therefore we have we can read R naught from a UV cutoff there. From this expression, it's clear that when Q equals 0, then it reduces to the expression we had before. Now here's a question: is there any other way to probe behind the horizon to find such an expression here? You know, this was some this expression based on some assumption and some some computation, and there is there another way to find such an expression from another perspective? That's the question. And moreover, if you expand this expression or the neutral case for very tiny UV cutoff, when the UV cutoff is small, this is the expression you get for relation between two cutoffs. R naught is a cutoff near the singularity, and RC is cutoff at the UV cutoff. They come with different power. Is there any way to understand why they come with different power? But to address or to understand this thing, we consider another way to probe behind the horizon and to see if we can get such an expression. Okay, in the context of ADS-CFT correspondence, there are several attempts to construct operator on dual field theory to describe the interior of the black hole. In particular, in this paper I showed here, there are several descriptions, several proposals how to construct operator which is dual to field behind the horizon. Although there are serious concerns on the state dependent of this construction, it is found useful to examine the cutoff behind the horizon in this context. Of course, in the case we are considering, which is an eternal black hole, it is better understood. This construction of this people is better understood. Okay, let me just briefly review how to construct some operator which is dual to field behind the horizon. Let's start with a free field or free field in the field theory side, whose modes in the momentum space are denoted by O omega k. Then one might define a conformal field theory, a non-local operator in conformal field theory in this expression, by this expression here. And this is non-local in the sense that it depends on some extra parameter R, which at the end of the day, we want to identify with the radial coordinate of ADS. And for appropriate choice of function f, this operator has the same correlator as free field propagating the region defined by 1 in this bulk space. Actually, this has, for the massless case, it has to satisfy the Laplace equation here. And if you have the Laplace equation, then we have some non-local field which correspond to some local field on the boundary, on the bulk, and which has same correlators for region 1. Similarly, one may define the same similar expression for the field describing this part of the spacetime. And in order to describe an operator behind the horizon, it turns out that one needs 2 copies of these operators. More explicitly, more precisely, for an operator behind the horizon, one has the expression. We have 2 modes and denoted by O and O tilde. And to have the operator behind the horizon, we need both of them. Remember that in this case, when we are in the region 1 and 3, there is only one propagating mode, but here you have two propagating mode, and both G and G tilde, here G1 and G2, satisfy a Killing-Gordon equation for Fourier scaling with the smooth boundary condition. When we go from region 1 to 2 or 3 to 2, there is a smooth boundary condition there. So in this context, intuitively, one would also expect that the setting UV cutoff at the boundary would automatically restrict the range of the space-time associated accessible to the field defined behind the horizon. This is a resembling of the phenomena we already see in the complexity. Remember that there was some non-locality parameter here, or there was a non-locality operator here, and this non-locality parameter is associated with the bulk. Therefore, that it tells you that how deep the field should be defined when you have when you have this non-local parameter here. Therefore, when you add some cutoff here, which restricts somehow this non-locality, it means that somehow you are restricting the deep of the radius of the ADS. Therefore, there could be some relation here. Now, for these operators I define here, I want to compute the partition function. One can go and compute the partition function. For region 2, which is this one may compute the partition function in this way, and rewriting this in terms of the momentum mode, we get something expression. At large and limit, one may decompose the above partition function in this way. And this is also, if you see for large and this can be decomposed here. Of course, this S is different than this S. Remember that the action is different, but we get such a decomposition here, which means that the partition function of region 2 is given by the partition function of region 1 times the partition function of region 3. Since I am assuming in this case that region 1 and region 2 are identical, therefore in this case, what we get is the partition function of region 2 is proportional to the partition function of region 1 squared. And if you use ADS safety correspondence, means that in the bulk, one you have to look at the action and unshell action in two different parts should have such a relation here. Of course, I want to have an equality, not proportionality. Therefore, I will compute this unshell action in two different cases, one with cutoff and one without cutoff. And therefore, we get some equality here. It means that the variation of action here with and without cutoff is twice of in region 2 is twice of those that in the region 1, with assumption that region 1 and region 2 are identical. Now, for the case we want to compute this field I introduced. I suppose that this field is a linear dilaton, is in the graviton. Therefore, we want to compute unshell action for graviton there, which is unshell action of the action here. So we want to compute unshell action in region 2 here and region 1 here, with and without cutoff. If one compute this unshell action, this is what we get for region 1, and this is what we get with region 2. And equating this to expression, what we get this expression. This is exactly what we got from complexity consideration, and therefore the picture seems consistent. Let me conclude here. To summarize, we see although we have not fully understood the holographic complexity in the context of ADS-safety correspondence, it seems that it's useful quantity, the complex useful quantity to probe the region beyond the horizon. In this context, we have seen that as soon as we fix a UV cutoff, we are enforced to have a cutoff behind the horizon whose value is fixed by the UV cutoff. For the charged black hole, as I told you, there was two possibilities to put the cutoff behind the horizon, either behind the inner horizon or between two horizons. But we saw that putting the cutoff between two horizons get a consistent picture. Therefore, it seems that the complexity cannot probe behind the horizon. Holography, one might naturally identify this as a version of the strong cosmic censorship arising from holography and from complexity. If this picture is correct, it means that the near singularity modes may be regularized by the UV cutoff, and you don't need to add extra cutoff behind the horizon while setting it by hand. The relation between UV and behind the horizon cutoff is consistent with the fact that to describe behind the horizon, we need 2 copies of the outside the horizon fields. Okay, that's what I wanted to say, and thank you for your attention.
Thank you very much, Mohsen, for your talk. Any questions or comments? We finished a bit behind the time, so a bit earlier, I mean. So any questions from the audience? No? So it seems that everything is clear. So in that case, we can conclude the session for today, the first half of the presentations, and we are going to meet in about 2.5 hours. So thank you very much, and see you in 2.5 hours. Okay. Thank you.
Okay, thank you. Bye.
Bye.